The signal came in quietly, almost unnoticed, folded within a sea of numbers, nestled in the infrared glow of a star 120 light-years away. It was a Tuesday morning in December, ordinary in every way, except for the fact that everything was about to change. Somewhere deep in the constellation, Leo, a planet had just whispered its existence in a language written not with words, but with light. And far away on Earth, in a chilly Cambridge University lab, a researcher named Niku Madusan leaned closer to his monitor, sensing the weight of something historic. Light travels at 186,000 miles per second. But even at that unimaginable speed, it still takes 120 years for those photons to cross the interstellar void and reach us. The photons that Niku was analyzing that morning had left their source, a red dwarf star called K2-18. Back in the early 1900s, they passed the orbits of gas giants, glided silently beyond the Oort cloud, slipped unnoticed through the darkness of interstellar space, and finally landed on the golden eye of the James Webb Space Telescope, orbiting quietly at the gravitational balance point called L2, a million miles from Earth. James Webb Space Telescope's massive mirror, made of 18 hexagonal segments coated in pure gold, captured the faintest hint of that alien sunlight. Some of that light had passed through the atmosphere of a planet, K2-18b, as it transited its parent star. In that brief moment, the planet's gases left fingerprints in the starlight, and Webb, more sensitive than anything built before it, recorded them all. Niku stared at those fingerprints, represented as spikes and dips in a spectral graph, each marking a chemical absorption in the alien air. At first, it was routine, water vapor, a promising but not uncommon find. Then methane and carbon dioxide, gases that, on Earth, often accompany biological activity. But then came a spectral signal that stopped his breath short, a molecule that should not have been there. Dimethyl sulfide. On Earth, this molecule is almost exclusively produced by living organisms, especially plankton in Earth's oceans. It's not something you'd expect to find drifting in the atmosphere of a lifeless gas giant. The signal was strong, too strong to dismiss. The statistical model, rerun 5 different ways, came back again and again, 99.7% certainty. Not a glitch, not a fluke, not noise. His hands trembled slightly as he stared at the screen. The numbers were clear, but the implications were not. Could this be life? Not a hypothetical, not a maybe, not a someday. Life, real and active, right now, on a world orbiting a star 26 trillion miles away. He blinked. His coffee had gone cold. It didn't matter. Niku wasn't alone in this. A team of international researchers, some in Geneva, some in Tokyo, others at NASA's Goddard Space Flight Center, had all been monitoring K2-18b for months. Each time the planet passed in front of its star, more light poured through its atmosphere. Webb recorded it, filtered it, and sent it down in coded bursts to Earth. And each time, the data grew louder. The story became clearer. This wasn't just a world with clouds and chemicals. This was a living world. The first whispers of the discovery leaked through scientific circles cautiously, almost fearfully, because the implications were too grand, too heavy. If this was real, it would mark the first time in human history that we found definitive evidence of life beyond Earth. But even more surprising was what kind of planet had sent this message. K2-18b is not Earth's twin. It is far from it. At over 8 times Earth's mass, it's classified as a super-Earth or a mini-Neptune. For years, astronomers assumed that such planets were too large, with too thick an atmosphere and too wild a climate to support life. But that assumption, like so many in the young science of exoplanet research, was crumbling. This planet, it seemed, had everything. A stable orbit in the habitable zone of its star, a thick hydrogen-rich atmosphere that kept its surface warm and pressure stable, water vapor, methane, carbon dioxide, and now dimethyl sulfide. Back in his lab, Niku exhaled deeply and whispered to himself, "This changes everything." He knew what would come next: reanalysis, peer review, skepticism, headlines, debates. But deep down, he also knew this was the beginning of something far larger. Not just a paper, not just a discovery, but a turning point in human history. People once looked up at the stars and wondered whether they were alone. Now, for the first time, there was a reason to believe they weren't. The weeks that followed were a storm of hushed excitement in observatories and research institutes around the world. The name K2-18b began appearing in late-night calls, confidential preprints, and private Slack channels buzzing with cautious wonder. But for those truly paying attention, the clues had been building for some time. Long before the dimethyl sulfide bombshell, the James Webb Space Telescope had already been feeding scientists tantalizing hints about this distant super-Earth. The first discovery was water vapor, clearly, strongly, and undeniably present. That alone would have made headlines in another time. Water is essential to life as we know it, and its presence in the atmosphere of an exoplanet orbiting a red dwarf was no small deal. But K2-18b wasn't done speaking. The second transit brought confirmation of carbon dioxide, then methane. These three molecules, water vapor, carbon dioxide, and methane, are all linked to life on Earth. In our biosphere, they're produced and cycled by plants, animals, bacteria, and even the weathering of rocks. Of course, none of them alone is proof of life. They can all exist through abiotic processes too. Volcanoes, comet impacts, chemical reactions deep within the crust of a planet. All can mimic the signs of biology. Still, there was something about the balance between them on K2-18b that made astronomers sit up a little straighter. On Earth, when these gases exist together in a stable ratio, it's because life is actively maintaining that balance. Methane and carbon dioxide should destroy each other over time. But if something keeps replenishing both, like biology, then they persist. The same seemed to be happening on K2-18b. Each new observation by Webb refined the models. Transit after transit, it added more detail to the atmospheric fingerprint. And with each pass, the pattern became less like noise and more like a symphony. This wasn't just a random mixture of gases. This was the structure. This was chemistry shaped by something. Astronomers call this kind of atmospheric profile a biosignature, a set of chemical conditions that, taken together, suggest not just the possibility of life, but its ongoing activity. And while many planets had shown maybe one-day hints of biosignatures, K2-18b's composition was louder, clearer, and more complete than anything ever detected. The media picked up the scent quickly. Articles began to circulate. "Super-Earth might be habitable," one headline read. "Life in a hydrogen world," asked another. But behind the scenes, scientists were scrambling to understand what kind of life could survive, let alone thrive, on such a world. Because K2-18b is no Earth clone. It orbits a red dwarf star, which is smaller and cooler than our Sun. This means the planet has to orbit much closer to remain warm enough for liquid water. And it does, completing an orbit every 33 Earth days. But this closeness also raises concerns. Red dwarfs are known for their stellar flares, bursts of high-energy radiation that can strip atmospheres or sterilize entire worlds. Yet, K2-18b's atmosphere appears intact. stable, shielding? The answer lies in its size. At 8.6 times Earth's mass and roughly 2.6 times the radius, its gravity is immense. This helps it hold onto its thick hydrogen envelope, dense, deep, and resilient to stellar outbursts. That same atmosphere protects any surface liquid from sudden temperature swings or radiation spikes. But the key moment, the reason scientists kept staring at the spectral data in disbelief, was the molecular signature of dimethyl sulfide. On Earth, this gas is mostly emitted by marine plankton. It plays a role in cloud formation, climate regulation, and the sulfur cycle. In fact, when you visit the ocean and catch that faint salty scent on the wind, that's often DMS you're smelling. But on K2-18b, its presence was baffling. There are no known non-biological processes that can produce it in large amounts, and the amount found there, confirmed across several transits, was substantial. This molecule didn't belong in a sterile, lifeless atmosphere. It belonged to life. Once that piece was in place, the atmosphere of K2-18b began to feel more like a planetary breath, an exhalation shaped by biology, a living world, speaking in chemistry. Webb had given us a planet that met all three conditions of the so-called Goldilocks zone model. Liquid water, check. Water vapor confirmed. Atmospheric stability, check. Hydrogen dominated, thick enough to redistribute heat evenly. Energy source, check. A calm, consistent red dwarf pumping out light for trillions of years. But most importantly, it had something Earth's neighbors never gave us, a biosignature we could measure from light years away. K2-18b's atmosphere didn't just suggest the conditions for life, it pointed directly at it. And as the world began to hear whispers of the discovery, scientists quietly began preparing for the next phase. Verification. More transits, more spectra, cross-checks with other observatories, confirmation of Webb's findings using Hubble, and possibly even future Earth-based telescopes equipped with infrared capabilities. Because the stakes had never been higher. If K2-18b truly housed life, any form, even microbes, it would mean that life wasn't rare. That biology could emerge in hydrogen-rich, high-pressure environments under alien skies. And if it could happen once, 120 light-years away, it could happen millions, billions of times across the galaxy. K2-18b wasn't just another exoplanet anymore. It was the first voice in a cosmic chorus we've only just begun to hear. The first time the dimethyl sulfide signal was confirmed, Niku Madusan sat in silence, hands resting on the arms of his chair, as if afraid that any sudden movement might scare the data away. It wasn't the excitement of discovery that overwhelmed him. It was the gravity, the weight of what it meant. The universe had just spoken in a whisper that only machines could hear, only software could interpret. And it had said something very old and very simple. I am alive. Dimethyl sulfide, DMS, is an unassuming molecule. On Earth, it floats invisibly over the oceans, released by tiny single-celled organisms like phytoplankton as they go about their lives. You smell it when the tide goes out, when the salt water warms on rocky shores, when a breeze carries that faint, tangy scent inland. It's not rare here, but finding it there, on a planet orbiting a distant red dwarf star 120 light-years away, was like finding a forgotten song from home playing in a foreign desert. The signal wasn't faint. It wasn't buried in uncertainty or statistical fog. It stood out in the data, clearly, boldly. A molecular pattern as precise as a fingerprint. It was as if K2-18b had drawn a circle around itself and written, in spectral ink, "Look here." Madusan's team triple-checked the raw spectra, The absorption line was right where it should be, at a wavelength consistent with DMS on Earth. The telescope's calibration had been perfect, no software glitches, no interference. They ruled out instrumental noise, atmospheric contamination, cosmic rays, and background sources. Every test pointed to the same outcome. The signal was real. But the question lingered in the air like fog. Could DMS be made by something other than life? That was the first instinct of every careful scientist. Skepticism, not celebration. Extraordinary claims, after all, demand extraordinary evidence. So, they dug deep. They looked for known abiotic processes that could create DMS. Volcanic activity? Not plausible. The temperatures on K2-18b's surface would likely suppress such reactions, especially under a hydrogen-rich sky. Meteor impacts? Too infrequent. Ultraviolet photochemistry in thick hydrogen atmospheres? Modeled and ruled out. The pathways simply didn't add up. None of the known chemical reactions, under any plausible planetary conditions, could explain the DMS concentrations they were seeing. And that's when the realization began to settle in. There weren't any good alternative explanations. The simplest answer, the most likely answer, was biology. Now, to be clear, no one was suggesting little green people swimming in alien oceans or waving from mountain ridges beneath hydrogen skies. What the data pointed to was microbial life. Simple, ancient, robust. The kind that had dominated Earth for over 2 billion years before complex organisms ever appeared. Single-celled, perhaps floating in a vast, warm sea under a gentle red sun. Organisms that might be releasing gases into the atmosphere, just like Earth's plankton do. It was poetic in its simplicity. A planet heavier than Earth, covered by deep oceans and a thick insulating atmosphere, hosting microbial life beneath a dim red sky. But there was another reason the DMS signal hit so hard. It wasn't just that the molecule existed on K2-18b, it was how much of it there was. On Earth, DMS is usually found in trace amounts, parts per billion. But on K2-18b, the levels were far higher. Not wildly so, not enough to suggest a planet crawling with visible life, but enough to imply that life wasn't just barely surviving. It was active, widespread, persistent, and it wasn't acting alone. The DMS existed alongside methane, water vapor, and carbon dioxide, molecules that, when combined, create a kind of chemical dance that's hard to maintain without help. Methane should break down over time in the presence of UV light, but something was replenishing it. DMS too should degrade, but it didn't. The ratios were balanced, sustained, rhythmic. In short, the chemistry wasn't static, it was alive. This is what scientists mean when they talk about disequilibrium biosignatures. In a lifeless world, chemicals eventually settle into balance, a sort of chemical silence. But in a world with biology, that balance is disturbed constantly. Life breaks the rules. It creates an imbalance. It injects energy into the system. And that was exactly what JWST had detected. The news began to ripple outward from research teams to scientific agencies. NASA, ESA, CSA, the Royal Astronomical Society. Peer review papers were submitted under heavy embargo. Webinars and briefings were held in quiet, password-locked digital rooms. Everyone understood the gravity. No one wanted to get this wrong. There had been false alarms before. Remember the excitement over phosphine on Venus? A controversial signal eventually walked back. The community had learned its lesson. This time, no one would cry wolf. But in private, many whispered what they dared not say aloud, that this was the one. The telescope had delivered what centuries of speculation could not: direct evidence in the form of light, that life might exist beyond Earth. It was no longer a fantasy whispered under starlight. It was a line in a spectrum, a spike on a graph, a reality so big it could barely fit in the human imagination. And yet, it was just the beginning. K2-18b was the first. But how many more were out there? How many planets had been dismissed as too strange, too alien, too unlike Earth to be worth looking at closely? The answer, it seemed, might be almost all of them, because life had just been found not on a twin of Earth, but on something else entirely, a hydrogen-shrouded world we never expected to understand. And that realization would soon crack open the cosmos. To understand why K2-18b is so extraordinary, you first have to unlearn what you think a habitable planet should be. For decades, we assumed that the best place to find life would be on Earth's twin, a rocky world with a thin nitrogen-oxygen atmosphere, orbiting a sun-like star at just the right distance for liquid water. That's what the textbooks taught. That's what our instincts told us to search for. But K2-18b shattered that model, because K2-18b doesn't have an Earth-like atmosphere, far from it. Instead, it's wrapped in a thick, hydrogen-rich envelope, many times denser than anything we breathe. And this, surprisingly, may be the very reason it can host life. Let's break that down. K2-18b belongs to a curious class of planets sometimes called hybrid worlds. It's too big to be considered a rocky, Earth-like planet, yet too small to be a full gas giant like Neptune. For a long time, astronomers weren't sure what to make of these super-Earths or mini-Neptunes. They were common in the galaxy, far more common than Earth-sized planets in fact, but many believed they were covered in gas, too hot, too pressurized, and utterly hostile to life. But that view has started to change. The key lies in their hydrogen atmospheres. On Earth, hydrogen is a trace gas, less than 1 part per million of our atmosphere. But on K2-18b, it dominates. Thick, light, and incredibly insulating, hydrogen behaves differently than the heavier gases we're used to. It doesn't just float off into space. It blankets. It holds in heat. It stabilizes. And on K2-18b, it may be doing something even more profound, creating a perfect greenhouse effect. Not the kind we fear on Earth, the kind that scorches and spirals out of control like on Venus, but a gentle, controlled greenhouse. One that keeps the planet warm enough for oceans to stay liquid, yet cool enough to avoid boiling them away. Imagine it, a planet more massive than Earth, surrounded by an atmosphere hundreds of times thicker, with temperatures hovering around 120 degrees, about 49 degrees. That may sound hot, but it's not lethal. In fact, many Earth organisms thrive in that range. And under those warm, heavy skies, liquid water could flow freely, perhaps in vast, dark oceans that span the entire globe. It's a kind of climate stability Earth can only dream of. Because hydrogen is such a light molecule, it spreads heat with incredible efficiency. That means the planet's night side, locked in perpetual darkness due to tidal locking, can remain almost as warm as the day side. No freezing poles, no scorching deserts, just one slow, balanced breath of thermal energy across the planet's surface. Even more fascinating is what happens when you peer beneath that atmosphere. Scientists believe that beneath the hydrogen and helium lies a vast layer of supercritical water, a strange fluid state that's not quite a gas and not quite a liquid. This could sit atop an ocean or a deep mantle of high-pressure ice. Now pause here. We're not talking about some tidy planet with continents and weather systems like Earth. K2-18b may have no solid surface at all, at least not one we'd ever stand on. Instead, Life may exist entirely in the atmosphere or in a band of water hundreds of kilometers down. Some scientists call this the Goldilocks layer, the region where temperature, pressure, and chemical ingredients come together just right for life to persist. And inside that invisible band, the chemistry is brewing. Water vapor, methane, carbon dioxide, dimethyl sulfide, all swirling together under a red sun. What's mind-bending is that this kind of world might be even better at hosting life than Earth. Our planet has sharp contrasts, hot deserts, frozen poles, violent storms. Life here survives by adapting constantly. But on K2-18b, things might be more gentle, stable, predictable. Conditions that allow simple organisms to thrive and persist for billions of years without interruption. That thick hydrogen atmosphere doesn't just protect the surface from solar radiation, it also prevents water loss into space. Unlike Mars, which lost its atmosphere billions of years ago and dried out, K2-18b has the gravity and gas retention to stay wet for the long haul. A kind of planetary thermos, keeping life cozy beneath its clouds. And that's the magic of it. For so long, we assumed habitability meant being Earth-like. But K2-18b has taught us that life might prefer a different recipe. Something heavier, something thicker, something more alien. In fact, the very qualities we once thought made a planet inhospitable, a massive size, a deep atmosphere, a red dwarf sun, might actually be advantages. More stable energy from a quieter star, more time for evolution under long-lasting conditions, more protection from space, less geological disruption, and more environments in which chemistry can get weird in all the right ways. As scientists updated their models and plugged in the new atmospheric data, one thing became painfully clear. We had been looking in the wrong places. Earth's blueprint was just one possibility. K2-18b was another. A world we never expected, now impossible to ignore. The telescope had pulled back the curtain, not just on a planet, but on a type of planet. A class of worlds that could be teeming with life, yet so alien we almost missed them entirely. And now, we'll never stop listening. If you could stand on K2-18b, though it's likely there's no true surface, you'd feel the difference immediately. Not just in the alien air or the strange reddish light of its sun, but in the sheer weight of everything. Gravity would press against your body like a slow, unrelenting tide. Your 150-pound frame on Earth, here you'd weigh well over 400 pounds, but on K2-18b, that crushing force might not be a disadvantage. It might actually be part of the reason life exists at all. The planet's mass, about 8.6 times that of Earth, translates into gravity nearly 3 times stronger. On most planets, that kind of pull would squeeze an atmosphere flat or pull it too tightly to allow complex weather systems. But K2-18b isn't most planets. That immense gravity is what allows it to hold onto its thick, hydrogen-rich atmosphere for billions of years, despite the tug of its nearby red dwarf star. While Mars's thin air blew away, K2-18b's stayed, wrapped around the planet like a pressure-sealed dome. To understand why this matters, think about how Earth's atmosphere behaves. It shields us from harmful radiation, redistributes heat, and keeps water from boiling off into space. But it's fragile. On Earth, a slight change in solar output or a small tilt in our axis can trigger global climate shifts. Ice ages, superstorms, mass extinctions. K2-18b, in contrast, is a planetary heavyweight. Its gravity pins everything in place, its atmosphere, its heat, and possibly even its oceans. This creates a stability we can barely imagine. This kind of constant life needs not just to appear, but to endure, to evolve, to experiment. So, what would life under 3 times Earth's gravity look like? Not like us. Here on Earth, gravity has shaped everything, from the wings of birds to the height of trees. In stronger gravity, evolution might favor compact, dense, low-profile organisms, creatures that hug the ground, that move slowly, that don't waste energy fighting the planet's pull. Plants, if they exist there, might be squat and fibrous. Microbes could dominate, floating in layers of ocean or air, designed not to soar, but to settle and survive. Swimming might be easier than walking, especially in a denser fluid, like hydrogen-enriched water, or even the planet's strange supercritical layers. Any organisms adapted to this world would be built differently from anything we know, more like jellyfish than giraffes, more pressure-tolerant than any deep-sea fish we've studied, perhaps transparent, perhaps chemically efficient in ways we haven't yet imagined. And while the surface gravity is intense, life wouldn't necessarily feel it the way we would. If these organisms evolved here, this gravity would be normal to them. Just as we take our own weight for granted, they might move effortlessly through their dense, pressurized world, completely unaware of how unusual their environment is from our perspective. In fact, the planet's gravity may help in another surprising way: atmospheric retention over geological time. Lighter gases like hydrogen tend to drift off into space on smaller worlds. That's why Earth doesn't have much hydrogen in its atmosphere. It simply escaped long ago. But K2-18b has the mass to hold on to hydrogen, preserving its thick shroud for billions of years. This stability provides a long-term climate system, less vulnerable to sudden shifts. And with time, life can do amazing things. More gravity also means more atmospheric pressure near the lower layers. That pressure could allow for complex chemistry to occur at rates we don't typically see on Earth. Reactions that take centuries here might happen faster there. Entire biological cycles could accelerate under the right conditions. It's even possible that gravity helps maintain a liquid layer beneath the gas envelope. Think of it like this. High gravity compresses the gases above, increasing temperature and pressure as you go deeper. At a certain depth, that pressure becomes just right to allow water to exist as a warm, dense liquid, creating a habitable layer that could support aquatic microbial life, similar to how hydrothermal vents on Earth sustain life without sunlight. And then there's the role gravity plays in protecting the planet. A thicker atmosphere doesn't just retain heat, it blocks radiation. K2-18b's red dwarf star, while stable now, might have been more volatile in its early years. Without the planet's intense gravity holding on to that protective hydrogen layer, flares and solar winds might have stripped the atmosphere away. But instead, it stayed intact, shielded, safe. Some scientists have speculated that even cloud ecosystems could form within the hydrogen envelope, regions of layered gases, floating moisture, and sustained chemistry. Think of it like the gas giants in our own solar system, Jupiter and Saturn, but scaled down, gentler, and warm enough to host life in the clouds. And that leads to one more twist. On Earth, gravity has always been a limitation, a force to overcome. We measure escape velocities, engineer rockets to break free of it. But on K2-18b, gravity isn't the enemy. It's the guardian. It's the quiet engine that keeps everything in place. The air, the warmth, the water, the chemistry, and maybe even life. For a long time, the search for habitability has focused on planets that mimic our own. But K2-18b is teaching us something vital. That difference doesn't mean deadly. That alien doesn't mean lifeless. And that a planet 3 times heavier than Earth might be more welcoming to biology than we ever imagined. The truth is, life doesn't care about what we find comfortable. It only needs the right conditions. And K2-18b, gravity and all, might just be one of the most welcoming homes in the galaxy. Let's drift now into the skies of K2-18b, the vast, layered alien skies. Picture a world where the clouds don't look like soft cotton balls, but rather stretch in bands and swirls, tinged in deep blues, subtle greens, and faint pinks. Colors born from exotic gases lit by a ruddy sun. The planet's thick hydrogen-rich atmosphere creates not just one sky, but many, stacked layers of gas, each with its own temperature, pressure, and chemistry. And within those layers, something astonishing may be happening. Because here's the strange part. Scientists aren't entirely sure if K2-18b even has a solid surface at all. Instead, it may have what's called a Hycean environment, a mix between hydrogen and ocean. Imagine a world where the planet isn't divided into land and sea like Earth, but instead transitions gradually from gas to mist to liquid, deeper and deeper until it becomes a warm, high-pressure ocean wrapped in a permanent, swirling fog. This is where the real magic begins. In this twilight world, somewhere between the upper cloud layers and the potential ocean below, conditions may be just right. Not too hot, not too cold, not too acidic or radioactive, for life to emerge. Not surface life, not trees or people, but microscopic, floating organisms. Life that rides the gentle updrafts, drifts on dense currents of hydrogen and vapor, and lives out its entire life cycle within a liquid gas envelope. Scientists call this possible zone the habitable shell. It's a Goldilocks layer, not too high where radiation from the star would fry organic molecules, and not too deep where pressure would crush anything fragile. It's a band, perhaps only a few kilometers thick, where liquid water droplets might form and stay suspended, like mist in the air. This is where water vapor detected by JWST becomes crucial. Because where there's water, especially in a stable layer like this, there's a chance for life. You might ask, but can anything really live in a cloud? And the answer is yes. Right here on Earth, above us, in our own upper atmosphere, we've found microbial life, real, living bacteria, drifting in clouds, surviving UV rays, freezing temperatures, and dryness. These microbes live, reproduce, and feed in the sky. They even help form raindrops by clustering around moisture, pulling water molecules together. It's called aeroplankton, and it might just be the model for what exists on K2-18b. Now scale that idea up. Replace Earth's nitrogen-rich sky with hydrogen. Add a bit of methane. Toss in the dimethyl sulfide signature that started this whole mystery. You now have a recipe, an alien one, for floating microbial life. Life that doesn't crawl or swim, but hovers, spreads, recycles, and endures. But what would these sky creatures be like? Imagine microscopic sacs filled with lighter-than-air gas, like organic balloons. Their outer walls might be made of something like lipids, greasy molecules that hold together even in hostile conditions. They could photosynthesize, not using sunlight the way plants do, but maybe pulling energy from faint infrared light or chemical gradients in the surrounding air. Others might feed on chemical compounds in the clouds, methane, ammonia, carbon dioxide, breaking them down to extract energy. Some might even glow. Bioluminescence is one of the oldest tricks life has invented. On Earth, deep-sea creatures use it to communicate, to lure prey, or to defend themselves. On K2-18b, where light from the red dwarf sun is dim, glowing microbes might light up like dust motes in a sunbeam, tiny sparks drifting through an endless storm. And with billions of years to evolve, they could form ecosystems, colonies, feedback loops, predator-prey relationships. Maybe they reproduce by budding or splitting. Maybe they drift in great spiral patterns like aerial jellyfish, congregating where the hydrogen mist is thickest. Of course, all of this is speculative. We're piecing together a puzzle with only a few corner pieces in place. But what's remarkable is how many clues point in the same direction. A red dwarf star giving off steady low light, ideal for long-term climate stability. A planet in the habitable zone. Water vapor, methane, and carbon dioxide, three of the key ingredients for organic chemistry. A thick hydrogen atmosphere that could insulate a habitable layer. A chemical marker, dimethyl sulfide, that on Earth is only produced by life. It's not proof, not yet. But it's the strongest case we've ever had. And even if these skybound life forms are simple, microscopic, or wildly different from anything we know, their existence would shatter everything we thought we understood about biology, planets, and ourselves. Because if life can exist here, in a pressure-cooked sky, on a mini Neptune, orbiting a red dwarf, then it's not rare, it's inevitable, and that changes everything. It means that the universe might be brimming with life in forms we've never imagined. Not just Earth-like worlds with continents and oceans, but gas shrouds, cloud cities, liquid layers, chemical currents. It means that biology isn't an Earth trick, it's a cosmic force. And so we look up into the swirling skies of K2-18b and wonder, are we watching a living planet breathe? Or better yet, are those clouds watching us back? The discovery of potential life on K2-18b wasn't just a scientific moment, it was a human one. The data was there, the spectral signatures, the chemistry, the physics. But what happened next wasn't just about telescopes or peer-reviewed journals. It was about people, and how we, as a species, began to process the idea that we might not be alone. The media broke the story on a quiet Monday morning. At first, only a few science outlets picked it up. Headlines were cautious. NASA telescope detects unusual chemistry on distant exoplanet, or new clues suggest possibility of life around red dwarf star. But within hours, the news exploded. Mainstream outlets began publishing bolder titles, signs of alien life. First solid evidence of life beyond Earth, a living world 120 light-years away. Suddenly, everyone wanted to know about K2-18b. Classrooms filled with questions. People stood around kitchen tables, TV screens, subway benches, talking. Was it real? What did it mean? Could these microbes one day evolve into something more? Could they know we exist? In Nairobi, a high school astronomy club watched a live stream of NASA's emergency press conference on a cracked projector screen. In Buenos Aires, a retired physicist cried in his apartment because this was the moment he had spent his whole life dreaming of. In Kyoto, two sisters stayed up all night discussing whether this meant the universe was full of gods or full of bacteria, or both. Even the Vatican issued a statement, not a denial, not concerned, just wonder. We are witnesses, one cardinal said, to creation still unfolding, and that is holy. Back in the scientific world, the data was triple-checked, quadruple-checked. Independent teams at ESA and JAXA confirmed it. The spectrum was real, the gases were present, and the odds of them appearing without biology were, at best, astronomically low. Still, caution ruled. No one said life out loud on record. Instead, the official phrase became anomalous atmospheric biosignatures consistent with biological processes, but the rest of the world just called it what it felt like. A signal. A quiet, indirect whisper from the cosmos. We are not alone. And in that whisper came an avalanche of emotions. For some, it was joy, a feeling of cosmic kinship. If simple life existed on a gas-wrapped world orbiting a cool red star, then surely it existed elsewhere, perhaps even intelligence, perhaps civilizations, perhaps friends. For others, it was fear. What if life was common, but dangerous? What if intelligence, once awakened, always led to war, extinction, collapse? What if K218b's microbes weren't the start of a hopeful story, but the only survivors of one gone wrong? And for many, it was humbling. Because for centuries, humans had built religions, philosophies, and dreams around the idea that we were special, alone, the center, the pinnacle. But now, those ideas were dissolving, molecule by molecule, in a hydrogen cloud on a distant world. Still, there was no panic, no chaos, just curiosity. NASA's announcement included new plans to target K218b with a whole wave of future instruments, polarimetry satellites to detect light-scattering patterns in the clouds, radio telescopes aimed toward the system, just in case any artificial signals slipped out, and atmospheric lander probes in the earlier stages of design. Of course, no ship could get there soon, not with our current technology. At 120 light-years away, even the fastest spacecraft ever built would take hundreds of thousands of years to arrive. It would be easier to colonize Mars 1,000 times over than to visit this gas-shrouded alien ocean. And yet, something about K218b awakened long-distance love. We couldn't reach it, couldn't touch it, couldn't know its creatures. But we could watch, we could listen, we could imagine. And imagination, more than any rover or rocket, is the thing that makes us human. In classrooms and cafes, people began to wonder aloud. What would K218b's night sky look like from the surface? Did those microbes evolve eyes or wings? Were they alone on their planet, or part of a greater, more complex ecosystem? Were they aware? Did they sense their star's warmth as we do the sun? Or were they simply organic chemistry on autopilot? No thoughts, no dreams, just slow dances of molecules in a twilight mist. Even that was enough. Because if even the simplest life had taken hold on another world, it meant that Earth was not the exception. It was part of a cosmic rule, and once that idea landed in the human mind, truly landed, it never left. Artists painted the alien skies. Poets wrote about ghost clouds full of breath. Songwriters imagined lullabies sung by floating creatures. Philosophers wrestled with questions they'd never been trained to ask. What rights does microbial alien life have? Could we ever visit without harming it? Should we? A new branch of thought emerged almost overnight: exoethics, the study of how humans ought to treat alien life, no matter how small, because no one wanted K218b to become the next Mars. No one wanted headlines one day that read, "First Earth bacteria found contaminating alien ocean." So for the first time in human history, we didn't just ask, can we go there? We asked, should we? And that question, gentle, moral, forward-looking, may be the surest sign that we were ready for this moment. Because the search for life out there was never just about them. It was always about us, about who we are, about who we might still become. The story of K218b didn't end with the discovery. In fact, it had only just begun. While the world's attention focused on the distant exoplanet's potential for life, teams of scientists behind the scenes had shifted their focus to a deeper question. Not just what was on the planet, but how it came to be. Because K218b wasn't just interesting for what it had. It was astonishing because of where it was. You see, K2-18b orbits a red dwarf star, a type of star that makes up nearly 70% of all stars in our galaxy. These stars are small, dim, and live for trillions of years, far longer than our Sun. But they also come with a catch. In their early years, red dwarfs are violent. They flare often, shooting out bursts of radiation hundreds of times stronger than anything Earth has ever endured. For a planet like K2-18b, caught in the delicate habitable zone, a region where water can exist as a liquid, this should have been devastating. Any normal atmosphere would have been blasted away. Any fragile chemicals, like water or organic molecules, should have been stripped off, leaving a cold, barren rock. But that's not what happened. Somehow, K2-18b held on. The planet's large mass likely gave it an edge. With a gravity more than twice that of Earth, it could cling tightly to its thick hydrogen atmosphere. That atmosphere, in turn, acted like a shield, buffering the surface from radiation, maintaining warmth, and creating a deep oceanic world below, one that could stay stable for billions of years. And in stability, life finds a way. Imagine this: far beneath the clouds, hidden under a layer of hydrogen gas and thick mist, there may be a vast liquid water ocean. It would be dark. No sunlight penetrates that deep, but it could be warm, heated from below by the planet's core or tidal forces from its parent star. And in that warm, pressurized sea, life could thrive. Microbial mats clinging to rocks, chemosynthetic life harvesting energy from minerals, maybe even complex ecosystems. In many ways, K2-18b resembles a scaled-up version of Enceladus or Europa, the ocean moons of Saturn and Jupiter, worlds we already suspect may harbor life beneath their icy shells. But K2-18b was bigger, warmer, and closer to its star. In some ways, it was even better suited for life than Earth. That idea alone sent shockwaves through the scientific community. Because if life could emerge on K2-18b, a world previously thought too massive, too volatile, too weird, then life could be anywhere. The cosmic filter that so many scientists feared, that narrow set of conditions required for biology, might be far broader than we imagined. Suddenly, the universe looked alive. Meanwhile, the search expanded. Other red dwarf systems were reanalyzed. Planets previously dismissed as too big or too cloudy were brought back into focus. Webb and its sister telescopes scanned the skies, collecting atmospheric fingerprints from across the galaxy. Hints appeared on worlds like TRAPPIST-1e, LHS-1140b, and GJ-12114b. Water vapor here, methane there. A strange dip in light from an exoplanet with unknown clouds. None were as clear as K2-18b, not yet, but each added another tile to a growing mosaic, a picture of a galaxy that didn't just contain the conditions for life, but embraced them. In time, astrophysicists began referring to K2-18b as the archetype, the first planet that taught us not only what to look for, but how to look. And in the labs back on Earth, something else was stirring. New proposals emerged for future missions, not just bigger telescopes, but interstellar probes, tiny spacecraft propelled by light sails, pushed by lasers, that could one day reach nearby stars within a human lifetime. The Breakthrough Starshot project, once considered too ambitious, found new momentum. If we couldn't visit K2-18b in person, maybe we could try its neighbors. Perhaps a closer red dwarf like Proxima Centauri or Barnard's star. Human curiosity, like light, doesn't stay still for long. And even though the journey to K2-18b would take thousands of years with current tech, the idea alone reshaped the way we thought about travel. Not as a race, not as conquest, but as a gift, a way to see ourselves in a larger story. It reminded us of something we had almost forgotten, that we are not the center of the universe, but we are part of it, a breathing, wondering, stargazing part. In the years that followed, new generations grew up with K2-18b etched into their childhood. It appeared in school books and bedtime stories. It was painted on the sides of science museums and embroidered into mission patches. Children didn't ask if aliens were real anymore. They asked, "When will we talk to them?" Or, "What color is the sky on K2-18b?" Or, "Do they dream too?" And even though we couldn't answer, it didn't matter. Because maybe the greatest gift K2-18b gave us wasn't proof of alien life. Maybe it was something deeper, a mirror, a way to look up at a star 120 light years away and see ourselves not as alone, but as one note in a song playing across the galaxy. A quiet, beautiful, living song. And we were finally learning to listen. The legacy of K2-18b was not only scientific, it was cultural, emotional, and profoundly human. After the initial shock of the discovery began to settle, something remarkable happened back on Earth. A slow, wide awakening. Across cities and continents, people started looking up again, not out of fear, but with wonder. At first, the excitement was centered on science. Schools hosted telescope nights. Parents tucked children into bed with stories not about fairy tale kingdoms, but about real worlds, like K2-18b, with its warm clouds and alien oceans. Artists painted swirling dreamscapes of life beneath gas canopies. Musicians composed symphonies inspired by the living planet, and poets tried, as poets always do, to capture the feeling of standing small beneath an infinite sky and realizing you are not alone. Some called it the second Copernican moment. The first had come when we learned that Earth was not the center of the universe. The second came when K2-18b whispered back through starlight, "You are not the only ones." And it wasn't just the public that felt it. World governments began holding summits, not to discuss borders or battles, but to talk about what comes next. If intelligent life is out there, how do we prepare? Do we listen quietly, or do we speak first? And what should we say? For decades, a message sat buried in the vaults of the Arecibo Observatory. A string of binary digits beamed toward a cluster of stars in 1974. Now, for the first time since then, serious efforts were underway to craft something new. Not just a signal, but a message that could speak for Earth, for all of us, in case someone out there was listening. But as humanity looked outward, something surprising happened inward. People began to talk, really talk, about our planet. K2-18b became a lens through which we viewed Earth itself. If we could cherish a world 120 light years away, how much more should we care for the only home we've ever known? Environmental campaigns surged. People started calling Earth the first living world, not just scientifically, but spiritually. Forests, rivers, and oceans became sacred again, not in a religious sense, but in a shared sense. A recognition that life, any life, was precious, rare, and worth protecting. And yet, amid the celebration, there were voices of caution. Philosophers reminded us that knowing life exists is not the same as understanding it. What kind of life might thrive in hydrogen seas beneath thick clouds? What do you think? Dream. Would it be microbial or something entirely different? Would it even know we existed? Others asked, if dimethyl sulfide was our clue, could we one day be recognized by our own planetary scent? What do we, as Earth, smell like from the stars? Ozone, oxygen, methane, and a growing list of pollutants, traces of our activity that no other world, so far, had shown. Were we not only being watched but judged? Could an alien civilization, scanning our world, see not just our brilliance, but also our mistakes? Still, most people chose hope. Because while K2-18b had sparked countless scientific papers, political debates, and philosophical essays, its deepest impact was far simpler. It united us. In Nairobi, a class of school children wrote letters to imaginary friends beneath the clouds of K2-18b. In Buenos Aires, a mural appeared, an enormous painting of two hands reaching across a sea of stars. In a quiet library in Kyoto, an old monk whispered, "The universe has folded a little closer to us." And in space, the James Webb Space Telescope continued its silent vigil, watching, recording, reaching. There was still so much we didn't know. What caused the planet's deep atmospheric stability? Was there a magnetic field shielding it? Did it have continents beneath its oceans? Or was it entirely water-covered? And most tantalizing of all, could there be intelligence? The idea of intelligent life on K2-18b was still, for the most part, speculation. Dimethyl sulfide was a biosignature, yes, but not a consciousness signature. There were no lights on the night side, no radio waves, no artificial patterns in its orbit. Not yet. But perhaps that was the point. Life doesn't always need to shout. Sometimes it simply breathes. And perhaps one day, far in the future, when our technology catches up with our imagination, we will find a way to go there, not just with photons and telescopes, but with ships and stories. We will descend through golden clouds, taste the hydrogen winds, dip robotic arms into alien seas, and whisper back, "We found you." And if something answers, even a ripple, a pulse, a light in the dark, then everything will change again. Until then, we listen, we wait, and we remember that the universe, vast as it is, has already said something beautiful. You are not alone. As the search deepened and the story of K2-18b spread from science labs to storybooks, humanity's tools evolved. New telescopes were designed, ones even more powerful than the James Webb. One of them was already being assembled in orbit, piece by careful piece, like a cosmic puzzle. It was called the Life Array, short for Large Interferometric Forensic Explorer, and its mission was simple: to see deeper, to see clearer, to see life. Unlike JWST, which could only observe distant planets through subtle spectral fingerprints, life was built to resolve exoplanets as worlds, not just dots. It would combine the signals from dozens of telescopes spread across thousands of kilometers, using interferometry to create a virtual telescope as wide as a moon. Its first target, you guessed it, K2-18b. While it launched, another mission stirred in quiet preparation. A new generation of ultra-fast, solar sail-powered probes was being designed, drawing on concepts from the Breakthrough Starshot initiative. These tiny, interstellar craft, no bigger than a loaf of bread, could ride beams of light at a fifth of the speed of light. It would still take decades to reach K2-18b's system, but for the first time in history, we had an engineering roadmap for sending something physical to a potentially living world. Humanity, once bound to Earth by gravity and uncertainty, was now building paths between stars, not of metal and fire, but of intent. And while the future unfolded, the present grew richer. Back on Earth, universities launched entire departments devoted to exobiology ethics. What would we owe alien life, even if it was microbial? Would it have a right to be left alone? Or would studying it justify intrusion? These weren't just theoretical debates anymore. They were the pressing questions of a species that might be on the verge of contact. Across cultures, ancient myths gained new relevance. The Zulu story of Nomkhubulwane, the goddess who connects earth and the sky. The Chinese legend of the Weaver Girl and the cowherd, lovers separated by a river of stars. The Navajo tale of the hero twins traveling through the heavens. Suddenly, these stories were no longer only about symbolic stars. They felt like premonitions of real ones. The universe wasn't just physics, it had meaning, and K2-18b sat at the center of it all, spinning silently beneath its ruddy star, unaware of how much it had changed the world 120 light years away. Or maybe not unaware. You see, one of the most curious findings from JWST wasn't the molecules, it was the motion. Subtle, repeated wobbles in the spectral lines suggested that K2-18b might not be the only body in its orbit. There was a whisper of a moon, not confirmed, not imaged, but hinted, a consistent gravitational tug, like a soft knock at the door. Scientists began calling it K2-18b-I, the first suspected moon of the system. And what's more, this moon might be rocky, it might be geologically active, and if it was orbiting a planet with a thick atmosphere and a stable climate, well, that opened an entirely new question. Was the life signature coming from the planet or from the moon? Maybe K2-18b wasn't the main act, but the stage. Maybe life was sheltering nearby, on a smaller, harder world with oceans and tides driven by the gas giant's pull. Just as Jupiter's moon Europa or Saturn's moon Enceladus are thought to harbor subsurface oceans beneath icy shells. Maybe K2-18b, I was the real cradle of life. And suddenly the story became a duet. Two worlds, a gas-wrapped giant and its hidden companion. One breathing gases into the void, the other circling quietly, possibly covered in ice or mist, or maybe something we hadn't even imagined yet. This is the nature of discovery. Every answer births 100 new questions. Every new question draws us further from certainty and deeper into awe. And yet, the farther we go, the more we realize we belong here, not just on Earth, not just in the solar system, but in the cosmos itself. We are, in the words of Carl Sagan, a way for the universe to know itself. And maybe, just maybe, K2-18b is another way the universe is watching back. As K2-18b and its possible moon stirred wonder and curiosity, Earth began to change, not just technologically, but emotionally. You could feel it in the quiet places, in observatories humming through the night, in long walks under star-filled skies, and in a gentle shift in the way people spoke about the universe. There was less loneliness now. Before, space had felt cold, silent, an infinite stretch of nothingness punctuated by blazing, unreachable stars. But now it felt like home was bigger. Earth was no longer a solitary miracle. It was the first note in a growing chorus, and this change began to shape the next generation. In classrooms, children no longer just memorized the names of planets. They imagined futures where they might walk on alien shores or float beneath unfamiliar skies. K2-18b became a symbol in textbooks, a poetic whisper in lullabies, and even the name of a new generation of space-based schools. One popular children's series, Cloud Song, told the story of a young hydrogen swimmer, a creature of the gas world who longed to see the stars. It inspired drawings, theatre plays, and even a ballet performed weightlessly aboard the International Orbital Arts Station. Because when the sky speaks, humans don't just listen, we create. Meanwhile, in labs and control centers across the globe, preparations continued. The Life Array was nearing completion. Engineers tested optical links in vacuum chambers, while data teams trained artificial intelligence to interpret interference patterns too complex for the human eye. They were training machines to look for life-shaped shadows, and soon they would point it toward K2-18b. But they weren't alone in their pursuit. Private companies, energized by the renewed space race, had begun to fund their own missions. Some focused on data, flying CubeSats through stellar alignments to pick up narrowband chemical traces. Others looked at propulsion, testing miniaturized engines capable of long-term solar cruising. But the boldest move came from a coalition called the Voyager Trust. Their proposal was as daring as it was poetic: to launch a message pod, not just radio waves but a physical object, toward K2-18b. It would contain languages, music, art, DNA samples, and a gold disc inscribed with a simple truth: "We saw your sky and believed it might hold friends." The project stirred debate. What if it attracted the wrong kind of attention? What if it interfered with delicate alien ecosystems? But in the end, it launched. Small, silent, powered by light. Not to arrive soon, but to begin a journey that could take a century or more. It wasn't about being heard immediately, it was about being worth hearing. At the same time, astronomers found something strange, again. As they studied the exoplanet's atmospheric patterns, they noticed an unusual rhythm. Fluctuations in infrared emissions that didn't quite match known models of planetary weather or photochemistry. At first, it was dismissed as data noise. Then, over several months, a pattern emerged. One that cycled in a way eerily similar to biological respiration. Could it be microbial clouds, blooming and fading with the seasons? Could it be something more organized? No one dared say the word intelligent aloud, not yet, but the papers hinted at it. Carefully, respectfully, with the kind of scientific restraint that disguises trembling excitement. The signal didn't repeat like a radio beacon. It didn't blink in prime numbers. It wasn't a message per se, but it was consistent. It had memory. It changed shape when starlight shifted, like something adapting, learning, responding. One researcher called it the breath of the cloud. Another called it the K2 rhythm. It could still be a natural process. The universe is full of surprises, but for the first time in human history, the possibility was no longer just theoretical. We were watching a living planet, and it might be watching back. In a quiet moment at Mission Control, one engineer, an older man who'd worked on radio telescopes since the age of copper wiring, stood staring at the screen. He didn't say anything for a long time. Then he whispered, "I wonder what their sky looks like." The room went still, not because anyone had the answer, but because everyone was imagining it. Clouds glowing with infrared light, 2 moons rising over a violet sea, a red sun trembling at the horizon like a low drumbeat, and maybe, just maybe, something beneath that sky looking up, wondering about our little dot in the dark, wondering if they too were alone. If K2-18b had life, then the chain of creation was no longer local, it was cosmic. Life might not be a fluke, it might be the rule. And if life could emerge twice, it could emerge 1,000 times. In that moment, a beautiful realization settled across humanity like dew on morning grass. The cosmos is not empty, it is unfinished. And we, tiny, curious, reckless, dreaming, are a part of that story. A punctuation mark in a sentence still being written. And so, on a pale blue planet 120 light-years away from the star K2-18, the question that had haunted humanity for centuries was no longer just if we are alone. Now it was when we would know for sure. The Life Array had completed calibration. Its arms stretched across orbit like a spider's web of mirrors, each one perfectly aligned to capture the faintest whispers of light from distant worlds. The target, K2-18b. For months it started. It gathered data from hydrogen lines, methane bands, carbon signatures. It mapped the shifting colors of the planet's clouds, measuring how sunlight scattered through them at dawn and dusk. And beneath it all, the machine watched for something far more elusive: structure. Because life, even simple life, leaves behind patterns. Not just molecules, but arrangements, ratios, symmetries, regularities that nature alone rarely achieves without intention. And one day, in the dark silence of data streams, the pattern blinked back. Not clearly, not conclusively, but enough. Enough for one of the lead spectrographers to freeze mid-analysis, push their glasses up their nose, and whisper one word to no one in particular. That's not random. The room filled quickly after that. Voices tumbled over each other, anxious, skeptical, disbelieving. They checked for errors. They rebooted systems. They reran calibrations. But the pattern held. It was subtle, nested in the ratios of trace gases at certain latitudes. A periodic increase and decay of specific compounds, cyanoacetylene, ethanolamine, isoprenoids, in a 27.5-day cycle. These were molecules that, on Earth, helped form the membranes of cells. And then came the clincher: chirality. On Earth, amino acids, the building blocks of life, are almost entirely left-handed. Inorganic processes produce both left and right-handed molecules, but life, it chooses a side, a preference, an imbalance. JWST had hinted at chirality. Life confirmed it. On K2-18b, there were molecules that were, impossibly, all the same handedness. Not only that, but they fluctuated with the seasons. The headlines were cautious. The word life appeared with disclaimers. But across the world, people felt the change, not because a voice had been heard or a photograph received, but because we saw a shadow, and it blinked. Governments met behind closed doors. Philosophers filled public squares. Artists painted skies they had never seen. And in quiet, vulnerable corners of the world, people stood outside at night and simply looked up. And then, the Vatican spoke. The Dalai Lama spoke. Elders in the Australian outback, griots in West Africa, rabbis in Jerusalem, priests in Kerala, tribal chiefs in the Amazon, all came forward not with fear, but with stories. Stories of ancestors from the sky, of cosmic kin, of creation that included not just humans, but others. Science had caught up to myth, and suddenly the world felt both larger and smaller at once. Still, many questions remained. If there was life, what kind was it? Was it like plankton, drifting lazily in cloud bands? Was it like moss, clinging to high-altitude particles? Or was it something wholly unfamiliar? A silicon-based. Inside them, scientists introduced Earth molecules, amino acids, lipids, sugars, to see how they behaved. And something strange happened. Under the conditions of K2-18b, Earth molecules behaved differently. Some broke apart, yes, but others assembled into new structures. They linked in spirals never before seen, formed bubble-like sacs that pulsed faintly under infrared light. It was too early to say they were alive, but they weren't dead either. All this while, the data kept coming. Life continued to observe. Other telescopes joined in, from orbit, from the Moon, even from Mars. Signals converged. Doubt evaporated. And finally, in a moment that would be taught in schools for centuries to come, a consortium of scientific bodies, NASA, ESA, JAXA, CNSA, ISRO, and more, issued a joint statement. It was one sentence long. The evidence strongly supports the presence of a living biosphere on K2-18b. Not proof, not contact, but confidence. And with that, Earth became different. Not geologically, not politically, but existentially. We were no longer a miracle. We were meant to better see the stars. Because in that vast ocean of dark, someone else might be looking back. And they too might be wondering, are we alone? By the time the announcement sank into the bones of everyday life, the Earth had already started to change. Not its rocks or rivers, but its spirit. It was subtle at first. Maps began to look different. Not because of borders or countries, but because a new dimension had entered the imagination. Vertical space, not up like planes, not orbits like satellites, but true outward. Street murals in Lagos and Kyoto now showed children pointing past stars. In Rio, a church replaced its stained glass with an artist's vision of K2-18b, swirling with sapphire mists. Schools rewrote their science curricula, but more than that, they rewrote their philosophy. Life is not rare, a new textbook in Nairobi read. It is woven into the fabric of the cosmos. It was now normal, common even, for children to ask not just what do you want to be when you grow up, but where do you want to go? Mars, Enceladus, or the far dream, K2-18b. Meanwhile, the wet world simulations grew more refined. What began as test chambers the size of swimming pools were now the size of small towns. Domes of engineered atmosphere, spinning to recreate gravity, pulsing with artificial starlight. Dozens of countries contributed modules. Inside, researchers lived full-time in sealed suits, tending to strange forms of pre-life. In one dome, a glistening purple mist self-replicated every 32 hours. In another, a carbon-based foam began building honeycomb patterns along the chamber walls, reacting to the shifting light cycles like clockwork. No one called these things life just yet, not officially, but in the silence of the lab, some researchers whispered to each other like they were in a cathedral. It's learning. But even as Earth explored K2-18b, a quiet realization was blooming among astrophysicists and exobiologists. If life could emerge on a gas giant's moon, around a red dwarf star, from water and carbon and trace gases, then life was not only common, it was ancient. K2-18 was a red dwarf after all. These stars burn slowly for trillions of years, far longer than our own sun will last. The star itself was nearly 8 billion years old, double the age of our solar system, meaning whatever life stirred on K2-18b had a head start. And that led to a new, unspoken question, one heavier than all the rest. Not, is there life, but, is there intelligence? The official line, of course, was no, nothing conclusive. No artificial signals, no Dyson spheres, no greetings in radio waves or blinking lasers. And yet, strange things began to appear in the data. Tiny fluctuations in the planet's thermal emissions, regular but asymmetrical. They didn't match any known weather pattern. A series of sharp dips in the infrared light curve, spaced too evenly to be clouds, and a peculiar ultraviolet glimmer near the planet's terminator, the line dividing day from night, that shifted position over time, like it was moving. It was all explainable, of course. Everything always is. But explanations began to feel more like comfort than clarity. And then one night, the Life Array captured something odd. During a transit, When K218b passed in front of its star, a new dip appeared. A small, sharp one, too fast to be on the planet, too smooth to be noisy, the kind of signal you'd expect if something else, something smaller, had crossed the star's face alongside the planet. Something structured. They called it Object Beta. It wasn't seen again. No repeat transit, no signal. Maybe it was a satellite. Maybe it was a passing moon. Maybe it was a shadow cast by something we simply didn't understand. But the community split into two quiet camps. Those who thought K218b hosted only microbes, maybe floating algae, maybe cloud-borne blooms. And those who whispered late into the night that maybe, just maybe, we had glimpsed the outline of technology. If so, it would explain the chemical regularity, the repeating bands of methane and dimethyl sulfide, the chirality, the seasonal variations, even the misty pulses in the upper atmosphere, because life might not just be surviving there, it might be thriving, it might be farming the skies, harvesting light, it might be watching us back. But what would we do if we knew? Would we speak? Would we wait? A great debate arose, quietly, behind the scenes. Ethicists, linguists, military advisors, theologians, and AI researchers all drafted possible messages. Some were friendly. Others are cautious. A few warned of silence. Still others argued that no message should come from Earth at all. Let the data speak first, they said. Let listening be the first contact. Because we were not yet ready, not because of war or politics or fear, but because we were still deciding who we are. And until we understood ourselves, how could we hope to understand another? Yet, deep in a small observatory atop a mountain in Chile, a postdoctoral student working the night shift did something very human. They stared at the blinking cursor of a command line, typed a simple message, and beamed it quietly toward K218b on a narrow, low-power signal. Hello, we are here. We are learning. We hope you are too. And then they sat back, alone beneath the stars, not afraid, not hoping for an answer, just listening. You're lying there, quiet now, eyes heavy, mind slowly melting into calm. But far above your resting body, far beyond Earth's blue cradle, humanity is not sleeping, because the search has only just begun. The confirmation of K218b's biosignatures, its methane, its carbon dioxide, its water vapor, and that mysterious whisper of dimethyl sulfide was only the first domino. The moment it became public, a kind of global gravitational shift began. The Decadal Survey, that 10-year blueprint for space science, was rewritten in weeks. Agencies across the globe fast-tracked their proposals. Congresses that normally argued over roads and budgets now quietly whispered about spectrometers, launch windows, and second-generation telescopes. Even nations that had never launched a satellite were now forming astrobiological committees. And not just for space. Universities are flooded with new applicants. Students who once wanted to be engineers or artists or lawyers, now dreaming of becoming planetary chemists, exo-oceanographers, interstellar archivists, or astroethicists. Because the question had changed from, are we alone? To something more profound. What kind of life will we meet? But as you drift in your blanket, Earth's engineers are staying up late. Some are designing telescopes 10 times sharper than James Webb, ones that can not only read a planet's atmosphere, but take images of it. Others are working on laser sails, ultra-thin mirrors that could be pushed by sunlight or microwave beams, tiny ships, small as postage stamps, that might reach K218b in 400 years. Yes, 400. But that's the difference now. We're not just thinking about lifetimes anymore. We're thinking in civilization time, in species time, the kind of time it takes to write letters, not just to our children, but to theirs, and theirs after that. A chain of hands reaching forward into the dark. Of course, skepticism remains. That's the job of good science. Some still say the signal is a false positive, that the methane came from volcanism, or the dimethyl sulfide was an artifact. Others say we must wait for second and third confirmations before rewriting our place in the cosmos. And they're right to be cautious. But caution isn't the same as inactivity. Even the skeptics are calling for better tools, more observation, more data, more listening. Because when the universe might be speaking, the only unforgivable thing is silence. Plans are already underway for a new generation of direct imaging space telescopes. One is called LUVOIR, the Large UV Optical IR Surveyor. Think of it as James Webb's big sibling, capable of blocking out the glare of a star to see the actual surface of an exoplanet. Another is HABEX, the Habitable Exoplanet Observatory, smaller but equipped with something astonishing, a starshade. Imagine a sunflower-shaped spacecraft flying tens of thousands of kilometers in front of the telescope, casting a perfect shadow, allowing Earth to peer into the secrets of nearby worlds without the interference of their suns. And both missions, if built, will target K2-18b first, because that planet is now the favorite. But it doesn't stop there. AI algorithms, refined, trained on years of telescope data, are now sifting through old observations with new eyes. And they're finding more candidates. K2-18b was never going to be alone. It just happened to be the first to hum with patterns that broke the silence. The first to remind us that the tree of life might have many roots, and that Earth is just one of them. The second and third are likely already known to us, lurking in raw data from TESS, Kepler, Spitzer and Webb, just waiting for someone to ask the right question. A chemical signature, a shadow too regular to be dust, a flicker in infrared no model can explain. These are the clues we now chase, not like hunters, but like pilgrims. And the pilgrimage has only just begun. And so, as you float there, your thoughts soft and sleepy, maybe you feel something you haven't felt in a long time, a tiny tingle of hope, not for rockets or flags on moons, but for something deeper, something gentle, a kind of cosmic companionship. And whether that life on K2-18b is slime or sponge, flower or fog, it doesn't matter. What matters is that life found a way, again, and that we were quiet enough, patient enough to hear it. That's the future now, not explosions or conquest, but listening. Not ownership of planets, but shared wonder. And now we arrive at the edge of the map. You, still curled up, drifting gently in your quiet space. The stars above you, twinkling through layers of atmosphere, pixels and dreams. And out there, across the vast ocean of dark, K2-18b waits, silent, distant, watching. But this isn't the end. It's something better. It's the opening line of a new chapter. When Earth first began listening to the stars, really listening with patient hearts and sharp tools, it did so with a sense of loneliness. The silence of the void felt heavy, like a door slammed shut behind us. Every exoplanet discovered was an echo, not a voice. But not anymore. Now, for the first time in history, we are writing a letter to the sky, and we believe someone might read it. A hydrogen-rich ocean world, wrapped in gas and mystery. A red sun casting bronze light on twin moons. A rhythm in the clouds that pulses like breath. And us, our tiny blue dot, whispering across space. We see you. That's all it takes to change the shape of a species. Not conquest, not invention, just recognition. You might wonder, will we ever actually meet them? Maybe not in your lifetime, maybe not in 100, but think of how far we've come since the telescope was invented, from Galileo sketching Jupiter's moons by candlelight, to us sketching the chemical mood of a planet 120 light years away. It's a kind of magic, but not the kind made of wands. It's the magic of persistence, of refusing to stop asking the biggest question, who else is out there? Even now, as you lie still and calm, data is streaming from orbit. The James Webb Space Telescope, suspended in its cold halo of silence, is still watching, still capturing those faint shadows, still feeding humanity's biggest craving: connection. In labs around the world, researchers are writing code to make machines understand exoplanet weather. Others are mapping soundscapes of distant worlds, turning atmospheric data into music, so you can hear what K2-18b might sound like. It sounds like fog over warm oceans, like heartbeat drums echoing through hydrogen, like a memory trying to remember itself. And the public? Oh, they've changed too. Not just scientists or dreamers anymore. Grandparents now name their grandchildren after stars. Children draw fish swimming in sky clouds on alien seas. Artists paint imagined cities clinging to gas giant moons. Philosophers ask, if we find life, do we owe it kindness, even if it cannot understand us? K2-18b has become more than a planet. It's a mirror. It shows us who we are, when we're not trying to dominate or divide or distract. It shows us humanity at its best, curious, brave, humble before the unknown. And when we look at it, we don't just wonder about them. We wonder, what will they see when they look back? So now, with a gentle breath and a gaze as wide as galaxies, you can rest easy, because the universe isn't empty. It's just waiting. And we, tiny, stubborn, wonderful humans, are finally ready to listen. To every molecule that doesn't belong, to every rhythm that doesn't make sense, to every flicker of light that might mean we are not alone. We're sending out our signals, our data, our stories, our songs. And whether someone out there answers in 100 years or 100,000, it doesn't matter. We've already taken the most important step. We believed they might exist, and in doing so, we found a new way to exist ourselves. And now, the stars have spoken, the questions have been asked, the answers still whispering in the dark, but for tonight, you don't need to reach for them. You can just breathe. The sky is wide, the galaxies are still turning, the planets are still dancing in their distant orbits. And you've taken a long journey, through oceans of gas, across alien moons, into questions older than fire and quieter than sleep. Let it settle in your chest. Let it glow behind your eyelids. The wonder, the calm, the knowing. Somewhere out there, a planet like K2-18b is turning. Maybe it has clouds the color of copper. Maybe its oceans reflect a different kind of sky. Maybe, just maybe, something is awake there too. Something that wonders, like you do. But you don't need to solve it all now. You don't need to understand everything. You don't even need to keep your eyes open. Just float here, in the stillness. The stars aren't going anywhere. The questions will be here tomorrow, and the universe is patient. So rest now. You've traveled far. You've looked deep. You've imagined what few dare to imagine, and that is enough for tonight. Let your breath slow. Let your thoughts soften. Let sleep come like a gentle moonrise over a distant sea. Good night, explorer. The cosmos will wait. Always.